Welcome to The Explainer. Today, we're going to take a journey to a place where numbers have a whole new dimension. A place where problems that seem impossible suddenly have these beautiful, elegant solutions. So, let's dive right in. What happens when the numbers you use every single day? Well, what happens when they just aren't enough to solve a problem right in front of you? Okay, take a look at this. Now, this isn't just some random problem from a math textbook. This kind of equation shows up all the time in the real world. I'm talking physics, engineering, anytime you're describing something that rotates or oscillates, like an electrical circuit or a vibrating guitar string, you run into equations just like this. They're everywhere. So you do what you're taught, right? You plug the numbers into the good old quadratic formula. And then, bam, you hit a brick wall. The formula is telling us we need to find the square root of a negative number. And we've all been told since day one in algebra that you can't do that. It's impossible. So is that it? Game over? Well, when mathematicians hit this same wall centuries ago, they didn't just give up. No way. They got creative. They figured, hey, if our number system can't handle this, maybe we need to expand it. Maybe we need a new kind of number. Their idea was simple, but honestly, it was totally radical. They said, what if we just invent a number to solve this? Let's create a number. We'll call it I for imaginary, and we'll define it as the square root of -1. Its one and only job is that when you square it, you get -1. That's its entire reason for being. And with this one new tool in our mathematical toolkit, that impossible square root of -16 is suddenly not a problem at all. It's just the square root of 16, which is 4, times the square root of -1, which is now I, so it's just 4i. And just like that, our equation that seemed to have no solution now has this perfect, beautiful answer. So this single idea gave birth to an entire new system of numbers. We call them complex numbers, and they have two parts. You've got the A part, which is just a regular real number we're all used to, and then you've got the B part, which is attached to our new friend, I. That's the imaginary part. And this is where you can really see the big idea. You know, real numbers live on a one-dimensional line, but complex numbers, they need more space. They live on a two-dimensional plane. We have a horizontal axis for the real part, and now a vertical axis for the imaginary part. We've literally added a whole new dimension to the very idea of a number. Okay, so we've got these new numbers on this new plane, but how do you actually use them? I mean, for this to be useful, we need to be able to do math with them, and it has to follow some consistent rules. Well, here's the good news. It's actually not that complicated. For addition, subtraction, and multiplication, you can pretty much just treat I like any other variable like x. You combine the real parts, you combine the imaginary parts, and there's just one special rule to remember. Whenever you see an I squared pop up, you just replace it with -1. Division, though. Division is a bit of a special puzzle. The goal is to get our answer back into that nice, clean A plus BI format. But if you divide by a complex number, you end up with an I in the denominator, which is messy. So how do we get rid of it? Well, this is where a really clever trick comes into play. The secret weapon is something called the complex conjugate. It sounds fancy, but it's super simple. For any complex number, A plus BI, its conjugate is just A minus BI. You literally just flip the sign in the middle. Geometrically, if you picture the number on the plane, its conjugate is just its mirror image across the horizontal axis. Now, here's why that conjugate is so cool. When you multiply any complex number by its conjugate, something magical happens. The imaginary parts completely cancel each other out, and you're left with a purely real number. And that's the whole trick to division. You just multiply the top and bottom of your fraction by the conjugate of the denominator. The bottom becomes a real number, and the problem is basically solved. So, we've got the rules, we know how to do the math, but what does all of this actually mean? We saw that complex numbers live on a plane, and this is where their true beauty, their hidden geometry, really starts to shine. So, look at multiplying in that A plus B form. It's messy. That formula works, for sure, but it doesn't really give you any intuition for what's actually happening. But what if we described our numbers on the plane in a totally different way? So instead of using x and y coordinates, we can pinpoint any number on the plane using two different things. Its distance from the center, we call that r, the modulus, and its angle from the positive horizontal axis, we call that theta, the argument. This is called the polar form. And here it is, The big aha moment. When you multiply two complex numbers in their polar form, all that messy algebra just melts away. The geometry becomes crystal clear. You just multiply their lengths and you add their angles. That's it. Multiplication in the complex plane isn't just a formula. It's a physical action. It's just rotation and scaling. This powerful geometric idea, this concept that multiplication is really just rotation, leads us directly to what many people consider the most beautiful and profound equation in all of mathematics. And I'm not the only one who thinks so. The legendary physicist Richard Feynman, he called it a jewel, and for a very, very good reason. This is it, Euler's formula. And what it does is, well, it's almost magical. It builds this perfect bridge between the exponential function e and the functions of trigonometry, sine and cosine. And what's the bridge made of? Our imaginary number I. In essence, it says that traveling around a circle is the same thing as raising e to an imaginary power. Now, this formula isn't just pretty, it is incredibly powerful. It leads directly to something called De Moivre's theorem. Because if we can write a complex number using e, then raising it to a power becomes incredibly easy. All that tedious algebra just disappears. It becomes simple geometry. You raise the length to the power, and you multiply the angle by the power. Done. And this works in reverse, too, for finding roots. So if we ask, what are all the solutions to z cubed equals 1? Well, we don't just find one answer. In the complex world, we find 3. And they're not just random. They are always perfectly and beautifully spaced out on a circle in the complex plane. You can see this stunning pattern right here. So just think about that. We started with what seemed like an impossible problem. And by having the courage to invent one imaginary number, we didn't just solve an equation. We unlocked an entire hidden geometric world. A world with unbelievably practical uses in everything from electrical engineering and signal processing to quantum mechanics. This whole incredible journey just started by someone asking, what if? It really makes you wonder, doesn't it? What other impossible problems are out there right now, just waiting for us to imagine a new dimension or a new number to solve them?